All right, so now that you've had a chance to do some video analysis of a pendulum, to discuss it on the forum, and to answer some questions where you were thinking about what your video analysis tells you, I want to take a few minutes to talk through what are the big ideas we want you to take away. So to help with that, I've got my work of doing that video analysis of the sample video we posted. So first thing I want to notice is the shape of these graphs. I've got my horizontal position time and my vertical position time graph up right now. So my horizontal is the blue, my vertical is the yellow. Now you'll notice the graph's a little rough, but they generally have this shape similar to, or the shape pretty close to a sine graph. So that's something that's going to be true of pendulums. Their position versus time graphs look like a sine wave. Now in physics we tend to get kind of sloppy about whether it's a sine or a cosine, because we can think of a cosine graph as just a sine graph that's been shifted over to give it a different intercept. And everything we already know about position time graphs is still going to apply. So like we know the intercept tells us the position at a time of 0, which is the starting point of the object. And so the intercept of my graphs here are telling me where that toy started relative to the origin. All right, now in math you probably learned about period as a term to talk about sine graphs. This is a term that we're going to use quite a bit as well. So if I think about the time it takes to complete one pattern, so if I look at my blue horizontal position versus time graph, if I start at this peak, I go down and get up to the next peak, that's one pattern, and that's around 1.5 seconds. I could also start at this low point, I could go up and get to the next low point. That also works out to be just about 1.5 seconds. Or I could even start at this middle spot. I could go down, I could go up, and get back to the next middle spot, which also is about 1.5 seconds. So as long as I've got one full pattern, it counts as a period, and the period is going to be the same no matter how you measure it. Now, if I compare my horizontal position time to my vertical position time graph, you probably noticed that your vertical graph has a much shorter period. In fact, about half. So if I go back to the video and think about the way that pendulum moves. So let me get about to the start here. As that pendulum, so the pendulum, it swings downward and then it goes back up. And so that actually is completing one vertical pattern, while it only completes half of a horizontal pattern. So a horizontal pattern is going to be starting over here, going to the right, and then going back left. Whereas a vertical pattern is just starting high, going low, going high again. And so every time it swings swings to the other side, it completes a vertical pattern. And so it's able to go up and down and up again twice before it completes one full swing away and back. And so that's why we see those different periods. Now I also want to think about the velocity versus time graphs, and I'm going to focus on the horizontal velocity graph because that's going to be the most relevant to where we're headed. So first thing I want to notice is this also has a rough sine wave shape. Again, it's not perfect. I got a little sloppy with some of my points, and then tracking something weirdly shaped like the Yoda toy tends to not give as clean of data as if I had some, I don't know, if I found something nice and round to tie on there instead. But I can still kind of see that sine wave shape. And if I check the period, like if I go from peak to peak, that is about 1.5 seconds. So I've got the same period on my horizontal velocity time graph as I do on my horizontal position time graph. And so it doesn't matter what quantity we're looking at, we have the same period. Now I can also think about the slope on this velocity time graph. We know that the slope of velocity time is acceleration. So that goes back to things we did earlier this year with velocity time graphs. And this sine shape, especially if I had something that was nice and smooth, that slope constantly changes. So that tells me the acceleration is always changing. That's going to be a really important idea. Now I'm going to put this on the same axes as my position versus time graph to help think through some things. So one of the things I want to keep in mind is that the slope of the position time graph gives us velocity. And so I want to imagine like holding a pen or a pencil tangent to this graph to see the slope. If I look at these peaks and valleys on my position time graphs, and so like this peak is when Yoda is furthest to the right. The valley is when Yoda is furthest to the left, so over on that side. So when Yoda's at the extremes of its motion. Now, if I imagine laying my pen or pencil along here, I would be able, that pen or pencil is going to lay like a horizontal line, which tells me the slope is 0 at those points. If I look at my velocity time graph, at those spots, my velocity is pretty much 0. So when Yoda's at those furthest extremes of his motion, his velocity goes to 0. Now, if I look at where the peaks and valleys on my velocity graph are, so when Yoda is traveling the fastest, that lines up with these spots in the middle on my position versus time graph. And that's going to be when Yoda is right in the middle of his swing, so at that lowest point. And that's when the velocity is greatest. And in fact, you'll notice when he's going one direction, the velocity is about 100 centimeters per second. When he's going the other, the velocity is about negative 100 centimeters per second. Now we know whether velocity is positive or negative tells us the direction of the motion. And so what this is showing, that Yoda is swinging from left to right, hits the maximum speed at that lowest point, and then starts to slow down as he gets to the extreme of his path and reaches a velocity of 0. And then he turns around and swings back the other way. So now he's swinging towards the left, and at that lowest point, gets to his fastest speed before he starts to slow down again until he reaches the extreme in the other direction. So there you have it, a quick overview of how to deal with position time and velocity versus time graphs for pendulums. Most of the ones we're going to be dealing with here from here on out are going to be nicely smoothed out, so they won't be as choppy looking as this velocity time graph. So you can imagine like drawing that nice sine curve that goes roughly through these points.